Okay, what we're going to do tonight is look at EIGRP, Enhanced Interior Gateway Routing Protocol. The reason it's enhanced, several years ago, Cisco had a proprietary protocol called IGRP. They've made it better, hence the enhanced IGRP. It's still Cisco proprietary, although I understand that they are allowing other people to use it. And the thing to remember when I say proprietary, we talked a little bit about OSPF, and we'll do more OSPF next time, multi-area OSPF. OSPF works on everything. EIGRP proprietary only work on that particular manufacturer. Okay, so the objectives for this one, the IP routing, differentiate methods of routing and routing protocols, administrative distance, and there's going to be two things in here. We're going to have administrative distance and then reported distance, or active distance, I think that they call it. They got some really kind of weird terms for EIGRP. And a lot of that is what it is. And we're going to configure and verify as a single autonomous system. I think that probably this, having taken CCNAs before, I seem to almost always have an EIGRP troubleshooting question. And one of the issues is going to be that they're going to be in different autonomous systems, so they won't work. These terms here, split horizon, we've kind of talked about that. Split horizon says that if an update came in on the interface, you won't send it out an interface. We'll talk about where that can be a problem. Metric and next hop. Metric, EIGRP, as somebody said in one of the courses that I had, it's the most complex metric in the world, but you don't have to really worry about it because you don't have to. It only uses two components of it, and you don't have to calculate it anyway. Next hop, we got that. Feasible distance, feasible successors, and administrative distance are things that we're going to look at in these things, in this thing tonight here a little bit. Feasibility condition, the sub-objective is not covered in this thing. Metric composition, the metric for EIGRP, and it is very complex. Router ID, we need one, and the only reason we really need it is so that the system can keep things sorted out. And just like we talked about router IDs before, it will use the highest IP unless we have a loopback, and then it'll use the highest loopback. The problem with just using an IP is things can change. And these protocols don't really update themselves unless you stop the protocol, restart the protocol, or restart the router. Typically what you do when you configure a router, you get up and running and you leave it alone because you don't want to break stuff. Loopback is good. We can also use a router ID in this thing. So auto summary, it's a little more than that, but what it really is super netting. And we'll see the impact on it when I kind of do the demos here. Load balancing, EIGRP does it. I'm going to do the whole lecture here, and then we'll go through the PowerPoints. Load balancing, we can load balance 4 equal routes on this thing. So once you get out, you can have 4 different interfaces that go out. Equal and unequal, it can do either of those. By default, it'll do equal load balancing, and if you don't configure it and you have unequal paths, it won't use both of them. Passive interface we've talked about before. We just turn off the advertising, in this case, of the protocol. That'd be something like if you had an interface and went to the ISP. You don't really want to advertise your internal network to the ISP and to the world. We'll look at a little bit of troubleshooting. The routing's enabled. This is IPv6. We have to enable IPv6 routing just like we did before. Correct path selection, troubleshooting and resolving EIGRP problems. I'm going to try to go through his procedure there. Autonomous system number. Split horizon. We got a lot of these objectives in here a couple of times, didn't we? EIGRP is classless. That means that we can subnet. But when we say we can subnet, it also does by default, except in packet tracer, a thing called auto summary, which means that if we had a bunch of 10 dot something networks with subnet masks, what it will do by default is say, hey, I have the 10 whatever network or the 10 network here. So it does an auto summary, unless we give it the no auto summary command, and we'll do that in the labs. Uses an autonomous system. An autonomous system is just a number that we're going to assign to it. What that means that it shares routing information, including the subnet mask, but it shares routing information only to routers that are a member of the same autonomous system. It doesn't matter what number you use as long as you use the same number on all of them in this thing. EIGRP is called a hybrid protocol because it has characteristics of distance vector and link state protocols. Distance vector protocols, and he uses the term in the book routing by rumor, which means that you find most of your information by listening to other people. So, you know, a friend told a friend that told a friend. Well, routers tell each other about the routes that can get to, and that's called a lot of times routing by rumor, and that's what we have here. Hybrid protocol. And sometimes it's called an advanced distance vector protocol, so you'll hear it both of those things. It does not send link state packets like OSPF. It does send hello packets, though, and finds its neighbors. It sends traditional distance vector updates. And I want to say traditional distance vector updates, sort of, because in RIP sent the entire route table every 60 seconds. Once EIGRP gets stable and gets all of the routing information that its neighbors has, it only sends changes. So there's a lot less information goes. It also uses multicast, whereas RIP used broadcast. It synchronizes the network topology information between the neighbors at the startup and then sends specific updates when the topology changes, same as the link state routers. So it only sends changes when they occur, and it's suitable for large internetworks, because when we get in, here is a proprietary protocol, I said that. When we get into this, it's going to have a route table, it's going to have a topology table. In the topology table, not a Tor table, topology table, it's going to have all the backup routes. So that if one goes down, it simply looks in the topology table and brings that route in. Now, there are going to be updates, obviously, because when the topology changes is when the updates happen. It's when it sends the information, new information out. Uses a dual algorithm. And the only thing you need to know about that, I think, is that it's called a dual algorithm to find the best path. Uses bounded updates, and therefore it reduces bandwidth usage. Bounded updates means only changes. And no broadcast uses the multicast to do those things. Before they can exchange routes, they got to become neighbors, and neighbors send hello packets and acknowledge packets. And when we do these things, I think once you establish an adjacency, and that's what they're called, adjacency, form adjacencies, they send the hello packet every 5 seconds. So we're going to have the hello packet interval as well as the, I won't call it the dead interval, but I think it's 4 times the hello. How long are you going to wait to get a hello packet from a router before you decide that it's not working anymore? 3 conditions for forming a relationship, a hello and an ACK. The autonomous system numbers have to match an identical metrics, K values, and we'll have a table in a little bit of what the K values are. And it actually only uses 2 of those K values by default. And one of the troubleshooting problems is going to have a K value mismatch. If you have a mismatch in these, if we don't have the identical metrics, it will not form the neighbor relationship. I think this is the picture out of the book. Before they can exchange their routes with each other, they had to become neighbors. There are 3 conditions. Again, this is the same one, but this is just a visual hello and a knack. And then we have a neighbor table. So we have a bunch of tables in here. We have the route table, we have the topology table, and we're going to have the neighbor table, which just tells you who your neighbors are. And all 3 of the things will be exchanged with directly connected neighbors. So if we had another router out here, this guy is not going to become a neighbor with it. These 2 will become neighbors, but only directly connected routers will become your neighbor. And once you become neighbors, you share information. And the routing by rumor happens is these 2 guys become neighbors, and they share route information. This guy knows about all of these connected, and he knows about routes that any routers down here have told him about. And he sends them to this guy. When these 2 become neighbors, he sends him the information. So he's actually sending information he doesn't have any direct knowledge of. Hence, routing by rumor. And the administrative distance is going to be increased, obviously, as we go from route. Well, these things are going to use a cost between the routers to determine which is the best route to get there. So they're exchanged every 5 seconds. It's the hello timer. The hold timer, see, I was wrong, for neighbors must match, otherwise the relationships keeps on changing. The hold timer is the amount of time a neighbor is willing to wait to receive a hello before the neighbor's dead. We're not expecting one. If the neighbor's dead, he comes out of the topology table, the topology gets updated, and you get new routes to everything. But it looks in the topology table for the backup routes when it does these things. We have some different distances here. Reported distance or advertised distance. And the reason that he talks about using reported instead of advertised, is we have administrative, which is also abbreviated AD, so it can get confusing if you have 2 ADs, administrative as well as advertised. What the advertised distance is the cost from the neighbor. And that's going to be in the topology table. The feasible distance is the administrative distance or the reported distance, let's call it the RD, plus the cost to the neighbor, which is really the total path cost. We have the neighbor table, which lists the tables, the topology table. Feasible successors are what the routes are called. Feasible successors are the backup routes. Successor routes, and he says think successful, are the routes that we use. So again, terminology is a little different in EIGRP than it is in a lot of the other ones. But we have a lot of tables in here that we can look at. And distances, and it's going to be a really big number. The distance is going to be a really big number, and it is based on the cost that we use for these things. So the reported or advertised distance, this is a metric of the remote network as reported by the neighbor. So what this really is the cost, the total cost for the neighbor to get to this location. It says, 2 advertisements to network 10. I wonder what my true cost is to network 10, because we got both of these guys going here. This one says your cost will be 1,000, and this one says your cost will be 1,500. This is the cost of the networks, and this is all based on bandwidth and delay. And this is something that's configurable on the interface. To get to the network 10, it will cost you whatever. So the cost is what it goes across here. So the advertised distance is what this guy tells us it's going to cost. And in this case, it'd be probably like a gigabit Ethernet or whatever that cost would be. So as we go through the rest of his, the routing table metric, and is the same as the second number in parentheses displayed in the topology table. So the advertised or Reported distance is going to be in the topology table, not in the route table. The feasible distance is going to be the one that's going to be in the route table. It should be the next one here. The feasible distance is the best metric among all the paths to the remote network. So this one's saying it'll cost me, okay, I lied before, saying 1,000. This guy is reported, this is the reported or advertised distance is 1,000. He says it cost me 500 to get to San Francisco and 500 to get to New York. Well, if that's going to be the case and this one's 1,500, the total cost here will be 2,000 and the total cost here will be 1,500, and the numbers are going to be a lot bigger than this when we get there. Don't worry about the size of the numbers, just what they are. So it's 2,000, so we're going to pick this route. Now, if they had been the same, since we could use both of the routes together, but since they're not the same, it's going to pick the best route. Again, a little bit later we'll see how we can do unequal routes. So we can do that. You could actually use both of these, and it would be a proportional amount of traffic. Most of the traffic would go on to 1,500. Some of the traffic would go on to 2,000 based on what was available there. So the metric is feasible distance, and the feasible distance, the one that we pick, is going to be the route, obviously the route that we're going to use. I'll lose my successor. It's going to be my successor route we get down here. So tables used by EIGRP. The neighbor table just tells you who the neighbors are and which ports they're connected to. The topology table is going to get the destination here in the topology table, the destination, the successor or the successful route, the one that has the best metric, is out of serial 00, so that's the one that we're going to choose. A feasible successor is a backup. Would work, but it's not as good as the other one is going to be this one here, which means that if this interface went down, for instance, it would automatically look into the topology table and say, hey, I have a feasible successor route. Let's just go ahead and use that one. And then in the route table, exit 000 is going to be the successor or the successful route. Depends on RTP, which is the Reliable Transfer Protocol. Again, it's another proprietary thing. It uses it to manage the communication of the messages between the EIGRP. The packet types, we can have an update packet, query. An update contains the route information. A query is that you request routes. If you've not been getting something, or if it loses a route, it can use a query in order to get it. And it's a reliable multicast. A reply is a response to a query, so these two go together. A hello message discovers neighbors, and the ACK message acknowledges the hello and the neighbor. So when we're trying to get going, we have a hello and then we have an ACK. And if the three things that we talked about are the same, then these two routers form a relationship. The diffusing update algorithm dual, and that's about as far as I can remember what you have to remember about that. It's used by EIGRP to select and maintain the best path. Dual allows EIGRP to figure out the backup route. We're going to have those. We'll see those. Supports VLSM, variable length subnet mask, which means that it sends the subnet mask with the topology information. Perform dynamic route recovery. Query neighbors for alternate routes and send out queries for alternate routes. If a route goes down and we don't have a feasible successor, it'll ask other routers if they can help it out to get a route there. EIGRP is quicker to recover because it has those feasible successors. If something goes down, it looks and sees if it has it, and it just puts that into the route table. OSPF has to do a regeneration, so it's going to be a little bit slower. That doesn't rely on just the one that we've talked about, table, neighbor table, topology table, and route table. So we're going to have all of those tables in there, and they're going to have different information. The neighbor table It's going to have the neighbor information, the topology, all the routes in the autonomous system are here. And the route table stores the ones that it's going to use right now. So the topology table has the successor and the feasible successor, the active and the backup routes are in here. And then configuring, let me just go through this, what he's going to do, and then I've got a packet tracer that we can try to go through his configurations with. So what we're going to do is the network that we have the 10s, and we have 24-bit subnet mask, which is going to affect us in the default of this thing because it does an auto summary, which each of these guys is then going to think it knows where everything is because it's the 10 network. We'll look at those. And you can use, if you want, this one uses 172.16, you can just use the classful subnet address. If we had a 192.168, we just have 192.168.10 network. That's the only thing that you have to advertise. So config T, router EIGRP, the autonomous system number. There's only, well, we got 3 routers here. We have to use 20 on each of these for the autonomous system number because they have to match before they're going to share any information. And what this does is says, hey, advertise anything, and this one, anything that's got a 10 in it, make it an EIGRP network, which means that, hey, you tell everybody about that network. Because remember back when we talked about the only thing that routers really know about for real are the things that are directly connected to it. It then tells the other routers about those routes, how to get there. Sends it out there, say, hey, to get to me, come out here, and then we will change the metric as we go through these things. Supports VLSM, automatically summarizes networks. To turn off summarization, no auto summary is what you have to do. Packet tracer, it appears to me, just doing the labs, does auto summary by default. It shouldn't. The does the no auto summary by default. Auto summary should be on, and I think that I have changed the configuration to where it does auto summary so that it'll actually react the way that he does. But it says if your router is attached to these two, the 10.10.20, the 10.10.30, they will be summarized as a 10/8, even though that they're subnetted with a 24-bit mask. Can cause problems if your networks are not contiguous. And non-contiguous means that we have these things separated by a different network type here. This one's separated by a 172. If they were contiguous, we probably would be in good shape with them. But we'll look at those. Discontiguous, the 172, the 10's here, and the 172 here is what makes this a discontiguous network. What it said, network 10's over here, network 10's over here. But since it does auto summary, each of them says that network 10, the entire 16 million addresses could be in that one process. Network selection, if we do the no auto summary in this thing, then it'll advertise the subnet mask. So what we really want to do in situations like this, and actually I think in most situations, well, if you're using the same networks, you probably want to turn auto summary off to do those things. Can load balance against unequal paths. If we had the unequal paths that we just looked at a little earlier and show IP route, we only see the one route in the route table, but if we look in the topology table, the successor and the feasible are there. It's a term called variance that allows it, and what this says is if we do a variance of 2, it will allow routes that are 2 times the cost of the successor route, which in most cases will get you with several routes. Split horizon, again, received on an interface from a neighbor, can't be advertised back on the opposite direction. It's on by default. The issue that we can get in with that, and in our network we have different ones, but if we had a network and we use sub interfaces, we only have one of these guys, and we use sub interfaces for the connectors on here on the single interface, then we could get in a problem, because the interface would say, hey, I got it on this, I got it, and I'm not going to send it out on this interface. So this guy down here wouldn't get any of this guy's routes because of split horizon. You can turn it off. And this is kind of what I was trying to say. Here's a route update on these things, the 10. Here's a route update. On these networks, this is fine because we have different interfaces. If we had a single interface coming in on this thing, it wouldn't send it out, and we would only get part of the updates. The configurations, and again, router EIGRP 20 network, same thing that I had earlier. I got some of these slides in here. 20 is the autonomous system number. Must have the same autonomous system number or they won't talk to each other. If you wanted to have two autonomous systems and you could do that, they would need different autonomous system numbers. Then the 20s would talk to the 20s and the 30s would talk to the 30s. You can use a wildcard mask if you want to, and back to that subnetting thing, the increment, if we had an increment of 4, for instance, then the wildcard mask, the increment is, the wildcard mask is the increment minus 1. So if we had a 25, which would be 2, 4, 8, 16, 32, 64 would be the increment, right? No, 128 would be the increment. I think 2, 4, 8, 16, 32, 64, 128, yeah. 7 bits. Then the wildcard mask would be 127, and you'd write it at 0.0.0.127. And again, in the wildcard mask, it ignores the zeros and checks the ones when we do these things. You can use one network command to advertise them all. Network 10, 10, 11. This would advertise the 10, 10, 11, and all of these things up here. You can advertise them this way by using the 0.0.0.255. What it's going to do is advertise the 10, 10, 11. You don't have, what it's saying is you don't have to do an individual network command for each of those. A passive interface won't send EIGRP updates out that interface. It can still receive them, unlike RIP, which won't receive or send updates. It uses multicasts to send it. This is the neighbor 172.16.2 neighbor. This happens if the neighbors don't form an adjacency. You can give a neighbor command. It's telling the corp router to use unicast instead of multicast, and multicast is spelled wrong here. If we do form the adjacencies automatically, it uses multicast. If we give a neighbor command, it will use a unicast message with it. I alluded to the metrics earlier, K1, K3, KT, K4. A table here, K1 is bandwidth, K2 is load, K3 is delay, K4 is reliability, K5 is MTU, maximum transmission unit. It actually only uses K1 and K3, and we'll look at that when we do the demo. And what it does is turn the bits on or off with a 0, 1, 0, 1, 0, 0. And there's another one in it that can only have a value of 0 when you actually make the change. But the metrics that it uses are bandwidth and delay, and you can change those configuring the interface if you want to, using the bandwidth command. Now this is different than no, never mind, it was clock rate. I get confused, losing my mind here. Maximum hops if we want to. 1 to 255 is the range for the hop, so this thing can go up to 255 hops. And what the hops for EIGRP really is how far down the line will it share its information. Different commands: show IP routes, show IP protocols, show IP EIGRP neighbors. This is the table that's in the book. These are the things that probably the only thing you're going to need to look at to do most of the troubleshooting you do in EIGRP. And the troubleshooting scenario that he has, the interfaces between the devices are down. This is the topology, much simpler topology than the one we're going to do the configuration. So we'll look at that, the K values. These are all the things that are wrong. The interfaces are down. The two routers have mismatching autonomous system numbers. I probably didn't do all of this stuff. Proper interfaces, some of the things to look for. This is not all the things that are wrong with the one we're going to do. Proper interfaces are not enabled for the EIGRP process. Passive interface. K values are mismatched. And if you have authentication configured, authentication turned on, it may be misconfigured. The number of those are going to be not all of those. A number of those are going to be in this little one here. IPv6. We have to turn on the unicast routing, and then we turn on EIGRP. After you do that, then they give no shutdown. This command is wrong, at least it's wrong in Packet Tracer, and he's got this in the labs. It's EIGRP router ID. You have to give it router, even though you're in the configure router, you have to tell it that it's a network ID for EIGRP. And then you go to the interface, and once you're on the interface, you take IPv6 EIGRP 10. So instead of up here like we did in IPv4 when we did router EIGRP and then we listed the networks, you go to each individual interface that you want EIGRP to run on and turn it on there. What this tells it to do is to advertise these networks. So we go to the interfaces, it advertises the networks and activates EIGRP on those interfaces. And this is, we'll do this step by step. These are just the commands that you use in here. Router ID, this serial, EIGRP 10, and it's kind of easier and it's kind of a pain. IPv4, all you have to have is, all you have to know is what the networks are that are directly connected, and those are the ones that you advertise, and you can do that with a show IP route before you do these things. Different commands for 6 protocols, very similar to what we had in the other one, the interfaces, neighbors, topology, protocol, and then they show IPv6 route EIGRP. It's going to show you the EIGRP routes. When we do anything with IPv6 in today's world, you have to specify IPv6, and again you have to turn it on before you get there. I know that was a drink with a fire hose, but hopefully we'll go through the configurations. Maybe all of that gibberish will make a little more sense after we go through how to configure these things.